Well, wonderful. Welcome, Rodrigo, and we're delighted to get to talk to you today. So thank you so much.
Thank you very much, McGill. So I'll start this up. Oops. And yes, so good morning to everyone. I guess it's late afternoon over here. So today I was going to tell you about the work that we've been doing, trying to use stellar streams from the Milky Way to understand how the Milky Way built up and the distribution of dark matter around it. And this is work I've been doing with this group of friends that I'm showing over here. And kind of what we want to do is to get a feeling of how to see what we can obtain in terms of the constraints on how the Milky Way built up, how the accretions came in at what time. We want to figure out what the role of the environment might have been, and in the end, what we'd really like to do is to place constraints on the dark matter distribution around the Milky Way and in other galaxies of the local group, and to try and confront that with theories of other theories of dark matter and gravity. So let's see if I can. So what I'd like to talk to you today then is summarized here. So I'd like to give you a brief introduction to stellar streams and how they pertain to the dark matter problem. And then I'm going to tell you about some work, the work we've done to find these structures. And then finally, I'm really very excited about the possibility now of using deep learning as a means to implement problems in dynamics. So I'll tell you about that towards the end. And so, as we all know, this is the picture that the current cosmological picture. Galaxies like the Milky Way are surrounded by these probably tens of thousands of dark matter subhalos. And inside of this, of course, we have our Milky Way, right? And with many cold, very fragile structures that are orbiting around here. And most of these subhalos, we know are not filled with stars, if this picture is correct. But nevertheless, they will have some sort of dynamical influence upon the dynamically cold structures in our galaxy. And so essentially what we'd like to do is to be able then to see, is this consistent, are the observations that we have consistent with the standard picture, or indeed are the alternatives for dark matter and gravity, can they also work? And of course, all of these theories, actually what they do is they predict accelerations. But generally, we can't actually go and measure the accelerations in the outer parts of the galaxies in the halo, just simply because the differences in velocity over time are very, very, very small. And so typically what people have done over the years, of course, is to implement equilibrium analyses, such as the Jeans equations and so on. And this works nicely. There are some for instance, Justin Reed and Fivos Diakogiannis and collaborators have made some very powerful pieces of software. But at the same time, we know that the galaxy is not an equilibrium structure. This has been shown very nicely by this the phase-phase spiral in the local disk. And so it would be nice to be able to understand to derive the acceleration field using some other means. And this is really where streams come into their own. And the point really here is that, of course, if we had the motions of stars through time, we would just obviously we would have the orbit of the structure, and then we'd immediately be able to derive the force field. Now we don't really get that with a stream, but what we get is as a stream. As the mass of the stream becomes smaller and smaller, what we know from embodied simulations is that the path of that stream on the sky resembles more and more the path of the orbit of the progenitor. And even though this isn't precisely true, we can always run n-body simulations to make the correction back to the orbit of the progenitor over time. So then this allows us to get the acceleration field. And so this sort of lists the reasons why we'd like to use stellar streams. Or very obviously, the structures that we now see are showing us how the galaxy built up over time. They give us this probe of the acceleration field for which we don't need to assume equilibrium dynamics. And they retain the sort of memory of their past interactions. And so as the progenitors orbited through the galaxy, they will have interacted with substructures within the disk of the galaxy, such as giant molecular clouds. They will have interacted with the bar, with spiral arms, and so on. And these retain these will influence the path of the stream, but still the information on the acceleration field is still kept, and also the information of these interactions. And something that a whole bunch of us almost 20 years ago proposed is that the streams are also these excellent accelerometers that can be used to probe whether the dark subhalos exist or not. And I'll come back to this in a few minutes. So people, because of these reasons and others, people have been trying to detect stellar streams for many years now, and the large sky surveys, the photometric sky surveys, came up with probably something close to 60 stellar streams before Gaia. And these show you the results from Sloan, from Pan-STARRS, and from the Dark Energy Survey. And basically, what the method that was used here was a matched filter analysis. So you have a template of the color magnitude of a system that you're actually trying to find. You have another color magnitude diagram of the contaminating Milky Way. You divide the template by the contamination, and that gives you a filter that then enhances the significance of the object, kind of optimally enhances those counts, and this is how you then are able to make these maps, or these sky maps, in which the star these stellar streams show up. So we thought this was very nice, of course, and I myself played this game of trying to find streams with matched filter techniques. But given the incredible power that we now have with Gaia, it seemed to me that there were better ways of approaching the problem. So basically, the question is, how do we best find streams in a data set such as Gaia's? And of course, what we have here is we have positions on the sky. We have parallaxes, we have problem motions, and some photometry for almost 2 billion stars now with Gaia EDR3, but only a small amount of information in terms of their radial velocities. And so we have this data set that is actually fairly heterogeneous in its quality in the different dimensions. And so essentially what we did was to implement a friend finder, where we look at each star in turn in the galaxy, and we shoot orbits using the Gaia positions and proper motions and parallaxes and photometry, which then gives us the distance. And we essentially marginalize. We shoot many such orbits that are consistent with these measurements. And to each one of these orbits, we smear them out in a kind of obvious Gaussian way, as is depicted here. And we do this, as I say, many times for many hundreds of different orbits for each star. And essentially, what we construct is a likelihood like this, where we have a stream model which contains all of these parameters, and a contamination, also a Milky Way foreground or background model that also is a function of all of these observables. And then what we do is we find the most likely fraction of stream stars and calculate for that most likely value of eta here. We calculate the likelihood of that star being a stream. So essentially, this allows us to make maps of streaminess of Gaia stars. And so if you do this using a kiloparsec wide or half a kiloparsec half wide template, so essentially how we smear out those orbits, what you get is this, and so it immediately shows up at super high significance, the Sagittarius dwarf galaxy. This is a really interesting structure for many reasons, also because I think it has some potential to actually to allow us to determine whether dynamical friction takes place, which is in itself kind of like a smoking gun of particle dark matter. If we use a much thinner template with DR2, with Gaia DR2, we found this series of 32 streams over the sky, which we then went and followed up with high resolution spectroscopy, both at CFHT and at VLT. And you can see that with the radial velocities that we obtained, these they show very, very clear kinematic coherence, showing that these structures are real. And the most recent maps look like this. So there's we're seeing this is showing us now the 10 sigma detections of streams in the Milky Way with a 50 parsec half width of these structures. In this case, between 3 and 12 kiloparsecs in the galaxy, and then going out now between 10 and 30 kiloparsecs. So again, finding these very thin streams. And as you can see, this the Milky Way has this lacework crisscrossing of these stream-like structures. There are many dozens of these at various levels of significance. And I could really give a talk on almost each one of these. There's one of them that is we found is the lowest metallicity, most pristine stellar system that has yet been discovered. There's over here, this is the stream of Omega Cen, which actually comes really, really close to us in the if we take another map of the at even closer distances. Given that we don't have all that much time, I'm going to concentrate for a couple of minutes on this stream here. This is the GD1 stream that has been studied in great detail by many people, and including Anna at your institute. And so, yeah, I'd like to spend a couple of minutes on this structure. And so the point here is that GD1 and these other objects can be used as a means to try and see whether streams are being heated by the cold dark matter substructures. And originally, when we proposed this idea back in 2002, we were thinking of a sort of kinematic heating. So essentially trying to see how the velocity dispersion changed along a stream. And that's the color here is showing us the radial velocity, and you can see that compared to the no CDM lumps case, you can see local heating of the stream. And Ray Karlberg a couple of years ago, actually almost a decade ago, suggested that instead of doing this, which is difficult to measure, you could try and find gaps in streams, and this has really taken on. Ray published in the initial works his study of PAL5 and suggested that maybe some of these apparent gaps here in PAL5 could be due to lambda CDM subhalos interacting with that stream. And for the case of GD1 though is really quite nice because it's apart from Sagittarius, well, among the thin streams that probably come from globular clusters, it's the most significant of the features out there. And in this paper by Binney and collaborators, they looked at the density of stars along the stream. So this is angle along the stream, along this GD1 stream. You can see it subtends a huge track on the sky of many tens of degrees. And curiously, it has these bumps and wiggles in the density profile. And so when they ran simulations in a smooth potential, they found, they're showing us here again as a function of angle along the stream, the counts, and you can see that the profile is quite smooth. As soon as you put in bars and spiral arms into this Milky Way model, you get something that is has some variations, but nowhere near what you see in the data. And so they use this. They use this data then of from Gaia along the stellar stream to construct these the density power spectrum of the arms in the leading arm and the trailing arm. And then this is shown here with these black dots. These are the data in the leading arm and in the trailing arm, and they're compared to models here, which are shown in these colored lines for embodied streams of different ages. Keep pressing this, of 3, 5, and 7 gigayears. And you can see here when they use only the baryonic substructures, the claim is that the lumpiness that you see in these models isn't as high as what you actually see in what you measure in Gaia. And it's only after you've put in after they put in the lambda cold-dark matter subhalos that you get something that approximates what is actually measured. And so they use this to claim that there's a significant number of cold-dark matter subhalos out there, about 0.4 compared to the predictions of CDM. So we looked into this as well, using the samples that came out of our own STREAMFINDER software. So having found the stream, we then measure the track of the stream on the sky. And what's shown in this diagram, so this is angle along the stream, and here we have the angle perpendicular to the stream. This is now showing us the 3 sigma detections here using only Gaia data in red, and the contaminants are shown in blue. And you can see that it's a very thin structure on the sky. So if we also include the information from pan-stars, we get a very similar diagram over here, very similar distribution on the sky. And these are very well behaved. These are very well behaved samples. If you go and measure the radial velocities along the stream of the stream members, you can see a very clear, very cold kinematic stream here in black. In proper motion and in the 2 components of proper motion, it's beautifully thin. And we also measure the distance to the stream using the pan-stars photometry, which is shown here with this fit in red. And incidentally, this is the parallel structure of the GD1 spur that Anna has been using in her work. And so we can then construct the density along the stream, which is shown in these. These are 3 different samples that we obtain from our own software, and then using essentially a very conservative way to construct a sample using only Gaia, and then Gaia plus pan-stars, and we obtain pretty much the same distribution in all 3 of them. And this is then the density power spectrum that we obtain, and it's kind of similar to what Binney and collaborators had found. you can see that it's reasonably flat as a function of inverse wave number in degrees. However, if we plot, if we have the distance to the stream, and we can then use that distance to correct this plot to the wave number in terms of kiloparsecs, and you can see that there's instead of being flat, we see this very large peak here at 2.5 kiloparsecs. And so this means that these bumps and wiggles, well, the spikes here, which are exceedingly which have very large contrast of up to 5:1, they all align with the same gap spacing, which is exactly what you expect of a system that is slowly disrupting. And whose stars are emanating out and then forming these epicyclic peaks. This is something that was explored in great detail by Andreas Küpper. And so what we think these are is not subhalos, but actually well, just simple epicyclic peaks from the progenitor just slowly disrupting. So now I can see I'm running a little bit late. So I'd like to tell you a little bit about the work we've been doing on machine learning, trying to use the streams in order to figure out what the transformation from angles from positions and velocities to actions and angles are. And so basically the idea here is that what we're doing is measuring, we're detecting streams in the Milky Way, but these allow us to get back to the orbit on the sky. And the point being that on an orbit, the actions remain constant. So can we use our observations to try and determine what the real actions of the stars are? And I'd just like to do a brief recap here of the action angle formalism. And basically what it is that there are these very convenient, very special canonical coordinates that instead of, for instance, if you have an orbit in normal position and velocity space, in action and an angle, this becomes really very simple. You just have a single action, and the different points along this orbit are then just different angles, and they're really very convenient because they're adiabatic invariants. And so essentially they're the best archaeological coordinates you can have for understanding the structures of the Milky Way. And so, for instance, as you, what the different actions mean, there's a J phi, which is just the Z component of angular momentum. As you increase JR, you can see this orbit here just becomes sort of more extended, has greater oscillations in the R direction, and increasing JZ gives greater oscillations in the Z direction. So these are very nice, very convenient coordinates, but the problem is they're very hard to find. And so essentially this was pioneered by McGill and Binney, who were the first to figure out an algorithm to measure these in general potentials. And so the way that the machinery works is that you start off with an action, and you're trying to get towards the positions and velocities. And what you do is you take a stepping stone via a toy system, which is just a simple isochrone. And you use a generating function for this canonical transformation, which is given here. And so so essentially what you're doing is you take an initial action, you use a whole series of angles on the in the toy system, and then this allows you to derive a series of, for each one of these positions in the on the toy system torus, you obtain a position and velocity in x and v space, and the algorithm then tries to make this aims to make the to obtain the same values of the Hamiltonian for each point in x and v space. And so there are some disadvantages with this technique. Basically, one of them is that you need to know the Hamiltonian in advance, and you can see that you're actually doing this backwards. Generally, what you want is to go from positions and velocities to actions and angles, and it actually goes the other way. And you might need quite a large number of Fourier terms to get this to work. And so what we did during the first lockdown was to develop an algorithm to do this in a completely automated way, where we go from the observed positions and velocities of points along orbits. We use then an analytic isochrone to go into into actions and angle space. And then what we do is the important step is to use a neural net for a generating function that allows us to go from this toy system into closer approximations to the real system. So the objective of this then is to obtain essentially flat actions here for each one of these orbits. And this works. And the very nice thing about this is that we haven't had to assume a functional form for the Hamiltonian or the potential, and indeed we haven't had to assume any symmetry. And once this runs, once you make a first run through this, you can also use it because you have once you determine what the actions are. You can just use the total derivative then to derive what the acceleration field is, and the reverse transformation is also completely possible. So how does this work? So we're comparing it here to the Torus machine, and with just 1,000 points, if we had 1,000 points in the Milky Way-like potential, we can get much better than 1% uncertainties. So, if we had 1,000 points in the Milky Way on orbits, so in this particular case, it was 128 orbits, each with 8 points. We get 0.4% errors, and very, very much lower errors if we increase the number of points that we're given. It also works for n-body simulations. We also tried it on some test orbits that have been defined by Sanders and Binney, and this shows you the evolution of the 3 components of the actions over time. This is integrated over 10 gigayears. In blue, we have the results of the Torus machine as implemented in our Gamma, and you can see that in many cases, in fact most cases, we do better than the Torus machine and a Gamma. One of the interesting points is that you can see each one of these in J5 is a straight line. That's because the Torus machine knows what the potential is, whereas ActionFinder has to actually discover that the system is axisymmetric. And so the basic architecture that's going behind this is it's shown in cartoon form here. Essentially, we have our data set, and we go through some sort of toy model. We implement a correction to that toy model in the form of a neural net, and that's then it's constrained by then the physics that we put in the form of differential equations. And I see I'm going way overboard, so
It's no problem. You can feel free to take your time, is what I'm trying to say.
Oh, thank you very much. So with my student Wasim Tanechi, what we're doing is trying to see if we can use exactly this this sort of machinery to then also apply these techniques to the field populations of the Milky Way. And so the idea here is to try and discover what the mass distribution is in the Milky Way or in dwarf galaxies. And so here we imagine it starting off with some real data in position and velocity. We use a trial potential. We start with some trial potential. We interrogate these points in that trial potential. Then we use our ActionFinder software to deliver the actions and angles corresponding to that data set in this trial potential. And then we use a normalizing flow to determine what the distribution function is in terms of the actions. We redraw random angles, and then use the inverse of the ActionFinder then to make random data sets in which which are completely phase mixed. Finally, we bring these things through to make a new distribution function here, which we can then compare directly to the observed data set via the Poisson likelihood. And then this thing here just goes round and round, updating the mass distribution effectively. So we're hoping to be able to implement this on real systems in the future. So just wrapping up, these stellar streams are, I think, are extremely useful as probes of the dark matter and of alternatives to CDM. What we're finding in the case of GD1 is that we believe we see that there are very periodic density peaks when you look at it in actual physical space along the stream rather than in angle. And we've developed this tool to make the canonical transformation between position and velocity and action and angle, which works in a completely automated way. And so essentially it's just learning this transformation from the physics rather than from examples. What's new about this is that we haven't actually needed to give it either the potential or the Hamiltonian, but it figures it out for itself. And it works it's set up to work with astrometric observables right now. But in order to actually get this to work on streams, we need to be able to provide the correction that allows you to go from a stream to an orbit. And so we need effectively embodied simulations for each one of these stream-like objects that we've been finding in the Milky Way. And in the future, what we intend to do, obviously, is to confront these observations with different theories of dark matter and gravity. But that'll come later. Thanks.
Thank you so much. Yeah, so towards starting a conversation, everyone ping me in the chat with a private message about the topic of your questions. Sorry, I was opening the chat at the same time as I was trying to speak. So I'm wondering if I can start things off with a little bit of a conversation about just the computational aspect of this. So it seems like at each step, we still need to integrate the ordinary differential equation of the orbit for many sort of trial objects to evaluate one likelihood in something like ActionFinder. Is that something that ends up being expensive when you're evaluating sort of a very large number of sources, or is that not a challenge?
So in fact, it doesn't. I mean, the idea behind it was to be able to use it eventually on real systems in the Milky Way. And so it doesn't actually integrate orbits at all. It's just using, it has, so, I mean, we do integrate orbits in order to test it. So essentially, when we give this this software a data set to try to recover the actions and angles that we know from some other source, we do actually integrate the orbits, but there's no integration within the algorithm itself. But this generating function is kind of complicated, and typically with something like 10,000 points, it takes a few hours to run. Okay. But it's really, yeah, the expensive part about it is that it's computing the well, essentially lots and lots of derivatives, because in the, I mean, it's all written in PyTorch, and so it's using the PyTorch automatic derivative engine, which is in fact taking second derivatives, and so yeah, that takes a bit of time.
Okay, amazing. So I had misunderstood some of the logistics of that, but that's wonderful to hear. Anthony, would you like to go ahead and unmute and ask your question?
Oh, so just for the sake of our rough understanding, what fraction of all the stars in the galaxy are in streams?
Yeah, that was a really interesting question, and I've been trying to look into that by kind of co-adding stars, so stacking them with a certain recipe to sort of get them all to match up along the same direction, and I think it's something like 3%, based on those games I've been playing. I haven't actually written that up, but essentially, if you just sort of take, you know, you take every Gaia star and then you try and you try and use say a photometric parallax to, or the actual measured parallax from Gaia to place them at a certain distance, and then you rotate them all so that they're all moving, say, in the x direction. So the proper motions are aligned in the x direction. Then you can just sort of stack them one on top of the other. And then you see interesting structure on different scales, actually. But it's something like 3%, I believe, are beyond what you'd consider to be possible binaries. And yet you do see a clear correlation.
Mm-hmm.
I mean, as a clarifying point, Rodrigo, by streams, you just mean coherent phase space structures, right? Like, you're not saying that 3% is from globular clusters. No,
I'm not saying that. I'm just saying that if you, yeah, so I guess it really depends what you mean by streams. So yes, if you, and this particular selection that I just mentioned was for stars that were beyond a certain distance, which I can't really remember, because I did this work a couple of years ago. But essentially, they were selected not to be in the disk, and so it's kind of a correlation between stars in the thick disk and halo, is what it would have been. But I think yeah, it's almost certainly going to change as a function of position in the galaxy, right? As you in some regions, I mean, probably all stars form in groups, right? And so at some level, there's going to be some correlation there, but eventually they get phase mixed, and you can't actually detect them as coherent structures.
So there's like a lifetime aspect to that question.
So there is a lifetime aspect, and in the halo, the time scale for this mixing is that much longer. Mm-hmm. I mean, if you were to ask the question, in the outer halo, then probably the fraction of stars and streams in the outer halo is quite high, because it's dominated by the Sagittarius stream, and then it's going to be dependent on metallicity too. So it's a difficult question to answer, I think.
So let's talk a tiny bit more about stream finding. Sonak, do you want to go ahead?
Oh, sure. Hello, Rodrigo. Thank you for a very interesting talk. I was wondering what you thought were the prospects of augmenting these stream finding algorithms beyond 6-dimensional information to include things like chemical abundances and those sorts of things that we might be able to measure with increasing precision with SDSS5 and stuff like that. So can these stream finding algorithms kind of fold in that kind of information to learn more about the progenitors of the streams, for example?
Yes, so I mean, currently it's set up in such a way that, I mean, as long as you provide a, I have updated this software several times to provide new information on, and so something like what we have can just we can just essentially append another probability, and so if you were to provide it with chemical abundances, which effectively just would imply an extra P to add onto the whole string of the ones that are currently there, then it would work in principle. The problem is that as the data set becomes less and less homogeneous, I think it becomes harder to interpret it, probably.
Okay, that's interesting to know. Thank you.
But I mean, I presume we're not going to have many of those stars, right? And so it's, I mean, one thing that we have been doing is, for instance, with radial velocities, for which we don't have many stars, but you can still use them to anchor down the orbital solutions, and so they're always very useful, right?
Yeah, I was kind of wondering it from almost the perspective of you obviously brought up the links with the nature of dark matter and how the streams can tell us something about that. And if you thought, for example, that dwarf galaxies and different theories of dark matter underwent slightly different kinds of star formation histories because of the manner of their formation, if that might in some way be imprinted in their chemical patterns as well. So
yeah, almost certainly. But I just see in terms of actually the detection of these objects, it might be hard to introduce that at the detection stage. I think if you have a sample of candidates, and then you're able to see to then bring in some additional information, then that allows you to then more easily determine whether the detection is what you thought it was. So I suspect that's probably more the way that we would tend to proceed, because that's actually happened with Nicolas Martin, who's been working with the Pristine survey, which is a narrowband survey in the calcium H and K lines, and which has some metallicity sensitivity. And so you essentially he took the detections that we found with the STREAMFINDER and then just cross-correlated them cross-matched them with his maps. And then you could pick out the structures that were very low metallicity. And actually, we managed to confirm pretty much all of these tiny little stream-like features that we'd found previously, because not only do they appear in the Gaia maps, but then they're confirmed as objects of a certain metallicity in the photometry.
Okay, that's really interesting.
Charlie, do you want to go ahead next?
Sure. So great talk, Rodrigo.
Thanks, Charlie.
As you know, there's been a lot of interest or realization over the last couple of years that the LMC induces a lot of large-scale effects in the galaxy, both, or predicted to at least, in terms of the shape of the potential and also movement of the barycenter relative to the outer halo. So how are you thinking about those effects in the context of modeling streams? You know, the effects on velocity and in terms of more complicated potentials. Just I'm curious of your thoughts on it.
The LMC is a real hassle, right? It makes life a lot harder. No, it's a very good point, and I think we're kind of hoping that for these inner galaxy structures, it's not too problematic. Clearly, it's not the case. Once you go out and I don't know, beyond probably something like 30 kpc, I mean, it doesn't make any sense not to take the LMC into account now. I'm hoping at some level we'll be able to get by with having a kind of like a perturbation, but yeah, so there are some people in our team, Simon Rosier, who's been kind of, he's been updating some the matrix method to try and figure out whether the trying to figure out the stability of the galaxy, and it's just pretty hard, right? Once the LMC comes in to model things correctly, and I suspect really nobody knows how to do this at the present day, right? And so, yeah, there was quite a lot of discussion in the Stream conference precisely about how we go about modeling the LMC, and I think it really is work in progress.
Okay, thanks.
What do you suggest?
No, I don't know. That's why I asked.
I think it's just hard.
Yeah, it's a hard problem.
Along the lines of hard problems, and to sort of mix things up a little bit. Okay, so I think Nelson, Caldwell, and Avi both have very related questions. So would you like to both unmute and you can ask your questions, and then Rodrigo can try to answer both all at once?
Mine's pretty short. So what's the difference between let's call it the Karlberg signature of subhalos and what you find in GD1? You know, is the wavelength, the depth of the gaps, the regularity? What should we be looking for in, say, other streams to identify subhalos as causing some structural differences in streams?
Well, I think, yeah, so the regularity is a bad thing, right? Okay. I mean, that suggests something else. So, I think that's that's one thing that we should be looking for. I mean, to be quite honest, I'm rather taken with Ray's picture, where at least some fraction of the globular clusters come in within dark matter subhalos, within small dark matter subhalos, because I really don't see why the halo globular clusters shouldn't be formed in some way like that, either in large galaxies or with their own dark matter subhalos, and in which case they sort of start disrupting before they come in, and then you get a whole mess, right? And so but at the same time, so even though I find that compelling, I think it makes it very hard to actually analyze them, right? Because they become very, very complicated structures, and so some of those, including GD1, we kind of think kind of resemble that picture. There's because GD1, I think I have it here. I'll just go back and yeah. So there's here's GD1, for instance, and there's this sort of parallel stream that has almost exactly the same the same actions, for instance, as GD1. And so they're clearly not systems that have formed, I think, in isolation, and they're not systems that are unperturbed. As Anna has shown, they're also there are features within GD1. There's this famous spur structure, which I think she's quite compellingly argued is due to an interaction with another dynamical, well, due to a dynamical interaction with another object. And we see also sort of parallel structures in several of these. I mean, these two objects here, for instance, have very close orbits. So all of that to say that I don't think we can get by with saying that the galaxy has a smooth potential. That just simply won't work. On the other hand, whether there are dark matter lumps, I think my own feeling is that it would be nice to take a sort of skeptical approach and see how far that goes. I mean, just how far can we try to push other sort of more mundane ways of causing the structures that we see in the streams. And so is there I think we're probably going to have to look at these in, as a population and to, but I don't think that there's a simple signature that we can say right now, okay, this nothing else would do this other than a CDM subhalo flyby.
Thanks.
I mean, I think it really has to be a sort of like a population study.
Right. Right. Okay, thank you.
Sorry, I was muted. Go ahead, Avi, along those last lines.
Yeah, no, so my question was, can we turn it around and perhaps constrain the nature of dark matter in the sense of CDM not being consistent with the lack of clumps that you would, because already it was 40%, and now you're saying, I don't necessarily see evidence for clumps in addition to the periodic structures. So the question is, can you say something about CDM not being compatible with the current data?
Well, yeah, I mean, I think one can go about doing that eventually. I mean, this work that I mentioned here was using the lumpiness that we observe and claimed that could only be due to the flyby heating. Now, turning this around, of course, I think requires because this is this after all is the default theory, right? I mean, and so it's much easier to convince oneself that something that everybody agrees on works. Actually, turning it around and saying that, the fact that we see, that we're able to produce these peaks, well, that they're very periodic when you look at them in the right way, and also that an n-body simulation can produce something that looks vaguely like that, which is actually shown in this lower diagram here. I mean, it isn't a perfect match to the lumpiness that we do see in GD1. We weren't able to make an n-body simulation that did that. It reproduces to some extent, but I think this is not enough. By any means, not enough evidence to throw out CDM. I think we'll have to go through this data set with a fine-tooth comb, looking at all of these objects, modeling them in great detail, probably modeling them also with, codes such as n-body 6 that taken, where you're able to follow but carefully the collisional aspects of the progenitors before one can make such a statement. So I think it's still years off, is my feeling, right? I mean, this certainly makes me feel uncomfortable with respect to these predictions by Binney and collaborators. I think they've done a very their modeling work, I think, is very good. I think they've jumped to conclusions, is my feeling, but but then turning that around and saying that it doesn't, that lambda CDM doesn't work is still a way off, I think.
Thank you.
Well, thank you so much. In these closing couple of minutes, we wanted to give you the chance to have the last word about, something you're excited about, something you're looking forward to, or just to wrap up the discussion.
Oh, I wasn't expecting that.
Or I can ask you another question.
Well, sure, go ahead. But
so do you anticipate an epoch where we have enough samples in something like ActionFinder to define the potential at a granularity that would inform our understanding of dark matter substructure? Right.
Oh.
So in a sense, like we could be noise limited, or like we could be resolving the potential. And I don't have a sense of like what it would take or whether we could ever get there with the available
well, to be
data.
honest, that's exactly what we intended to do with this, right? And so the idea with it was to essentially try, the potential on all scales, going from the very outer reaches of the halo all the way down to the size of the width of these streams, all throughout the galaxy. So I was actually quite surprised and pleasantly surprised that when I gave you the what we were obtaining for the uncertainties, for instance, on the actions. This is, we have more than 1,000 points in streams already. We have many more than that, right? I mean, this does actually require full 6-dimensional phase space information. But the radial velocities are easy to get once we've identified the stars. I mean, we don't have loads and loads and loads of radial velocities in general for these Gaia measurements, but getting the follow-up is easy. Distances are harder, mind you, and so I'm not entirely sure to what extent we're limited by a lack of distance information to these structures, which are typically like 10 kiloparsecs away. But that's certainly where we're going towards, right? That's and we're hoping that this this machinery will then allow us to do that, because it gives us essentially a means to provide. To build a neural net that represents then the acceleration field on all those scales. But there's lots of work.
It's extremely exciting.
But yeah, so the difficulty really is now in going from streams to orbits, right? And that will require some effort, and then correcting for all of these possible. All the flybys and stuff, and all the other complications.
Yeah. Well, that I think is an exciting note to end on. Thank you for sharing sort of all of these prospects and ways we can use these new methods to get a lot of insight.
Thank you ever so much for your questions. They're really very interesting.